Hello and welcome back, or simply welcome. If you have joined us only in the past few weeks, please check out our old material. We've covered so much. Our new chapter will be dedicated to the study of curves, not only in Euclidean spaces, but also in general metric spaces. Why? Because the curves are intrinsically beautiful geometric objects. Who doesn't love curves? And because they are useful in so many other branches of mathematics, particularly the notion of line integral, a way to define an integral over a curve, has applications in complex analysis, in ordinary differential equations where you have integral curves as solutions to the equations. They are even used in the theory of Sobolev spaces on general metric measure spaces if you follow the upper gradient approach. One of the references I will be using is a book on quasi-conformal mapping theory, and that deals with the theory of curves because they are central to that theory as well. The geodesic problem, the problem of whether there are always shortest curves between given 2 points in a metric space, is also very important. But also I chose this topic because despite its simplicity, its apparent simplicity, it will expose you to a lot of deep concepts in analysis and geometry. We will see absolutely continuous functions. We will see functions of bounded variation. We will see that the fundamental theorem of calculus can fail and what not. Okay, so a quick overview of what to expect. As every book does, we will cover change of parameter and arc length parameterizations. We will talk about curves that are defined on open intervals. And then we will talk about this length formula where you recover the length of a curve by integrating its speed. So we take derivative, you take norm of that derivative. Now this is a real valued function. You integrate, and hopefully you recover the length back. This is defined differently. This is not a definition. This is a theorem. And we will see that it does not always hold, but we will give sufficient and necessary conditions when it does. After that, we switch to curves in metric spaces. The most important notion will be that of some kind of derivative for these. And with that derivative, we will have this analogous length formula, which is just amazing because with no linear structure, how are you gonna find a substitute for this? Then we talk about geodesic problem in metric spaces. Both parametric version and also the intrinsic version where curves are not defined as parameterized from an interval, but rather as via intrinsic metric properties, for example, that they are compact, connected with finite Hausdorff measure. Then we define line integrals, and maybe we talk about one-dimensional area formula, though about that I don't make a promise. My main reference for the material before the metric stuff begins will be this amazing book by Jussi Väisälä. It's an old book, but it's amazingly well written and clean cut. In case I forget in future, my other references will be these books, especially the Ambrosio and Tilly will be our exclusive reference when it comes to the study of curves in metric spaces. In general, I will avoid proofs and technicalities. Number one, I don't want to copy paste books here. Number two, we want to talk about the notions and how they come together rather than details, which you can always find in the books. Or do as exercises, which is the better way of doing it. So let's begin by talking about curves. What is a curve? We have some intuition, or we think we have some intuition of what they are, but we must give a precise mathematical definition. The easiest one that does not require too much background, and that is the reason is given in undergraduate courses, is to define it as some function defined on some interval. The non-unique part comes from the fact that some authors already begin with Lipschitz curves or C1 curves, and that's where the variety comes in depending on the purpose and your audience. But anyway, we define these to be continuous curves on the intervals, and X will be a Euclidean space until we switch to arbitrary metric spaces. The good thing is that whatever works in Euclidean space pretty much makes sense in the Euclidean, in the arbitrary metric spaces as well, and I will point out these overlaps. Again, we don't have to have compact interval. We can even have the circle. And Leone's book does an amazing job of not starting with continuity assumption and then proving stuff actually about these intrinsic definitions through this Hausdorff measure I alluded to before. Okay, keep in mind that the curve is not a set. So you may look at this and say it is a curve, but under our definition, this is the image of the curve, and we don't know how it has been parameterized. Maybe you travel this much of it in just 1 second, and it takes 1 year to travel the rest of it. So that's a different curve than just going smoothly from one end to the other. The same set can have two parameterizations, which I just gave an example of. Also, you can look at a circle and not know that it has been actually traversed twice. So e to it and e to I2t are two different curves, and these are even more different than previous example in an essential way that we will see later. Their images is the same, but they are very different curves. One easy example of a curve is the graph of a continuous function. If you have a real valued function f defined on an interval, you can just put t and ft together and get a curve. By definition, it is a curve. Now, just requiring continuous function on an interval does not rule out some of the odd anomalies that we wish we don't have to include as curves. For example, the constant curve, which maps everything to the same point, by our definition is a curve, although it's, well, a point. On the other extreme, which is even scarier, is that there are some continuous maps from the interval whose image covers a whole square. And these are called Peano curves as well, because he gave the first example in 1890. So we don't want to say that this is a curve, so we have to find some way of taking that out of the admissible class. And it turns out the right notion to do so is that of the length of the curve. So this thick notation here is actually not that scary, because all it's saying is the following. You partition your time interval. That's easy because you just put some increasing sequence of points, finitely many. You're not partitioning the curve. That's important. And then you look at the images of those points. So my curve, by necessity, so that I can draw it, is a simple one, but you can have a constant curve. You can have the curve self-intersecting and also self-overlapping over a whole interval. For example, maybe this curve goes all the way to the end and then returns and covers it backwards. We don't care. The definition does make sense. And then what you what this summation is these successive distances. This distance plus this distance. And then you take supremum, which is you look at the worst, the largest number you can get. And even if that largest number is finite, you call this curve rectifiable, or you say that it has finite length, or you say that it is a bounded total variation. And the relation to the BV theory will be apparent in future videos. There are some immediate things you can see. For example, the length of gamma is at least the distance of gamma A and gamma B. Can you see how to prove it? Maybe 3 seconds. 1, 2, 3. You take the 2-point partition. You take T0 to be A and T1 to be B. That's it. And this is proven. But a nicer exercise will be that on the plane, prove that the shortest curve, okay, let's say this, length of gamma equals distance of gamma A and gamma B if and only if image of gamma is the straight line. So if gamma ever goes off this straight line, you will have a strictly bigger length. Why is my handwriting like this? It's often not this. Anyway, well, an interesting thing about this formula is that it is indeed, and surprisingly so, only a metric concept. The reason being that this quantity here is none other than the distance of gamma Ti to gamma Ti minus 1. It's just part of life that the distance in Euclidean space is given this way. Therefore, if you had just a map into X with only a distance structure, this definition would still make sense. That's why when we talk about rectifiable curves in metric spaces, none of these definitions will change, and everything will work verbatim. The next thing is that we don't require the endpoints to be in the partition, so the same definition works also if you have a curve defined on an open interval. We will have a theorem about that later. Notice that adding more nodes will only make this summation bigger, because if you add a new node here, now you go this way plus that way, and by triangle inequality, you cannot go down. You have to go up. The next thing is that I intentionally here drew dotted lines just to say that I'm looking at the distance, and I didn't draw these solid lines, which is what they do in some textbooks. That gives the false impression that what we're trying to do is to approximate the curve by piecewise linear curves. That is not accurate, because to do that, especially in an undergraduate course, you have to give a notion of what does it mean for a sequence of curves to converge to another curve, in what topology, in what metric. And once even you decide on this, then it is not really completely obvious whether simply being rectifiable, that means in this sense being of finite length, implies that there is a sequence of piecewise linear curves that converge in that topology to gamma. I don't know the answer to that for sure, but the point is, what we're doing here has nothing to do with this. It's a different question. All we're doing is just adding these distances. That's it. Next is some easy observations. For example, length of gamma can be 0 only if gamma is a constant curve, which is its image is just 1 point. And that follows from this inequality here. As soon as you have 2 distinct points, you take 2-point partition, and that gives you a positive number. So additivity over intervals is that the length of the curve, say from from A to C, plus the length of the remaining part of the curve, which is gamma restricted to C to B, add up. If you add them, the two up, you get the full length of the gamma. Okay. The ultimate goal will be to find particularly nice parameterizations of curves. Okay, that's the end goal. So we have to find a way to go from one parameterization to another and to be able to compare them. So let's say you have one curve, one parameterization. Let me use blue, from interval AB into your metric space Rn, Rd. And let's say this is curve gamma. Now, if you have a function h, which bijectively, so for now, let's say it bijectively just transforms this interval to a new interval. So AB becomes CD in a one-to-one bijective continuous fashion. Then this curve alpha equal sorry, this alpha so first of all, alpha, if you have gamma, let me yeah, that was correct. So what I'm doing is, because h is bijective, it has an inverse, so I can do this h inverse. So to know where this point maps to, I go backward with h to here, and then look where gamma sends it to. And if I reverse the order here, then this will be that gamma is alpha composed with h. So these two curves are related by a bijective change of their parameter, the time interval. And what is true is that they traverse the same set, exactly same image, but with different timings. So I think of h here as a time dilation. It just plays around with how, at what time the curve is at a certain point on the curve. So gamma and alpha are at different points on the curve as time passes. But the point will be that in this definition, we don't require h to be bijective. Now, what will happen is that h is continuous, increasing and onto, so it ends, the interval fills the other interval, but there could be some part which maps to the same point. And therefore, this h has no inverse, so it's out of the picture, so you only are left with this. Now, the point is, under this constraint, so if this is the case, if there is such an h, we say that gamma is obtained from alpha. Now, it's not the other way. We cannot say alpha is also obtained from gamma. So it becomes a one-sided thing. So gamma is obtained from alpha by an increasing change of parameter. The point is that alpha is a better curve than beta, than gamma. The reason being that we cut out this interval where it was constant. So for this whole interval, h goes to the same value, so alpha OH goes to the same value, so gamma goes to the same value. So this will be gamma of any point that is in this interval of constancy. Let's say call it J. And we don't like that about the curve often because nothing happens geometrically. So in going from gamma to alpha, we end up improving our curve. So we cut out unnecessary intervals of constancy. Okay, so our ultimate goal will be to get the best we can get, the best alpha. And alpha will be a reparameterization of gamma. And we will see that not just, well, alpha will have no interval of constancy. Furthermore, it will be parameterized by Arclength, but that is coming up next. But here is what was the key idea, that H doesn't have to be bijective. Bijective is easy. You just do a one-to-one correspondence between two intervals, and it's easy to go between two curves if you have bijection. So both of them are obtained from the other. But this nice definition from Weisel's book that I find quite elegant is that with this simple definition, he's able to prove the Arclength reparameterization, and that is the path I'm going to follow. Okay, I wish I could hear your questions and answer them, but you still have a chance to do so. Put them in the comments, and I'm always happy to expand more on these. Okay, so the goal will be start with a gamma and improve it to another curve. So some of these that will come, I have already mentioned. So they travel the same set with different timings. It is important that we allow, we don't require strictly increasing. Now, this is the point, that if your gamma is obtained from alpha by an increasing change of parameter as before, then the length does not change. And that maybe the picture helps you see why, because the only parts where H is non-bijective is the intervals of constancy. And there you don't obtain new length because you remain constant. Remember, we showed that length is 0 in a subinterval here, if and only if it remains constant. And from this example, we see that covering the circle twice is not related to covering it once through any change of parameter. Okay. Arc length. So toward this optimal parameterization that we have in mind, we define this real valued function. So you fix your curve, and for any time in that interval, you define the length that you obtain from part of the curve that is between A and T time intervals. Remember, S is not a curve itself, it's a real valued function. It's a number, it's a non-negative number for every T, and it is increasing. That is by definition of length as that supremum, because when T increases, you have more partitions to do and not less. Okay, the key lemma is that the distance between two values along the curve is less than the length between them. This is a definition of length, right? You take again the 2-point partition, and this is also pretty much how S is defined. So this is not a too deep lemma, but it has important consequences. For example, if S function is Lipschitz, for example, that means if there is some L, so that this is always less than this, then compare the first and last quantities, then this shows that gamma is also Lipschitz with the same Lipschitz constant. The less trivial observation is that the function s is always continuous. Remember, our curves are by definition assumed to be continuous. So two important facts about this length, arc length function. So s at t, the length of curve until point t. Okay, and here comes the arc length reparameterization theorem. Suppose you have a rectifiable gamma. That's the only assumption on gamma. It has finite length. Then there is a unique curve defined on some interval 0 to c, such that gamma is obtained from gamma 0 by an increasing change of parameter. So this goes back to our previous picture. So in particular, the intervals of constancy, for example, have been excised. So here is some h, and then that whole interval has become 1 point. So here is our original gamma. Here is our gamma 0. And gamma is gamma 0 composed with this h. And we cannot do the reverse. H is not always 1-to-1. Okay, so we go from gamma to gamma 0. It's another parameterization. And what is best about this gamma 0? Why is it the best reparameterization among all reparameterization? Is because I switch now the parameter name to s. The length of the new curve gamma 0, from 0 to s is exactly s for all the values in that 0c, which forces c to be the length of gamma. This is because of the previous thing. So proof of this last part will be that, remember we said that if gamma is obtained from gamma 0, their lengths are the same. So length of gamma 0 equals length of gamma, but a length of gamma 0 is equal to length of, well, gamma 0 from in all of its domain. And from the earlier part, from this, we see that this is equal to c. So c becomes equal to length of gamma. So for this second property, the only way you can obtain such a reparameterization is that c become equal to length of gamma. So it's gamma 0 is defined from 0 to the length of the original gamma. And yeah, so gamma 0, here is the thing. So here is the same image they share. Gamma itself may have intervals of constancy, but gamma 0 will not have. And it's from 0 to s will be, so gamma 0 will travel from here, gamma 0 of 0, and this will be gamma 0 of s. So it will be some other point there, but the point is that the amount that gamma 0 has traveled is exactly equal to s. From 0 to s, gamma 0 travels s feet, and for all s. And that is why it's called the arc length parameterization. And that's why we switched from t to s. So it's not based on time, it's based on the distance traveled on the arc length. So another way of looking at this is that gamma says, give me time, and I tell you where you are on the curve, on the image of the curve. So let's abuse this notation. But gamma 0 says, give me how far you've traveled, how long you've you've traveled, and I tell you where you are on the curve. Okay. notice that the relation between time t and s is not bijective. Different times may correspond to different lengths that you've traveled. At time 25, you may have traveled just as much as you had traveled at time 22, which forces that between 22 and 25, you didn't move at all along the curve, because any movement gains length. The only way so remember that length of gamma between any interval t1, t2 is bigger than the distance of its endpoints, gamma t1, gamma t2. So if s remains the same for t22 and t25, between these two, you had, if this is 0, there's no new length gained. This means this is 0. That means t1, gamma t1 and gamma t2 are equal. You can pick t1 and t2 between 22 and 25. And that is actually why it allows us to define gamma 0, because, okay, let me actually move on with this. And okay, this h here is the arc length parameter, in fact. So the change of parameter that happens allows this is exactly this function. So we know exactly what h is in that change of parameter. But the proof, so remember that you start with gamma and you need to define gamma 0. And here the point is, you cannot say gamma 0 is gamma defined with h inverse, because there is no h inverse, right? H is this length, and again, for some interval where function remains constant, all of that maps, so all of this t maps to the same ht. So if this is t0, all of these for every t is the same. So there's no h inverse. However, we force an inverse on h. What we do is that give me s, which is distance you've traveled, then there may be more than one time, more than one t, such that h of t is equal to s. Okay, the length you've traveled from a to 2 is s, and there may be more than one t, but then that forces that gamma was constant for all such t. Okay, then what you do is you define gamma 0 of this s to be gamma of that t, and whatever t you pick here, whatever t with h of t equal s. So you kind of reverse, you found an inverse. So t goes to s equal ht. Now s goes backward to t is not unique, but what I'm saying is it doesn't matter which t you pick. You can even leave it ambiguous, but the end result, this one, will indeed be well defined, because if you choose a different t, your gamma of that new t will also be equal to the previous one, because gamma was constant throughout that interval. So I will also have a pictorial description of this. So you kind of force an inverse. As I said, you just give me s. I found some t such that h of t is s, and it doesn't matter which t I pick. And that I call the function phi. Then gamma 0 you can define this way and then prove that phi 0 has all these properties. That's the proof. But before I give that picture, I promised there's also this nice observation that if you have two parameterizations that are related by an increasing change of parameter, then if you arc length parameterize each one of them individually using this theorem, the arc length parameterizations become the same. They both become from 0 to length. Remember, length of alpha and length of gamma are the same because of the previous theorem we had. And the interval is the same, and it turns out that everything is the same. So you get the same gamma 0. So gamma 0 and alpha 0 become the same. Okay, about the picture I gave you. Let me clean up some space to draw it. So we're talking about h. So h of t is length of gamma from a to t. So we've previously seen that s is increasing. So at a, it's 0. Okay, no length yet. It's increasing. It's continuous. So it goes like this. Being onto is just how you define this c to be length of gamma. So that's the trivial part. So this is your function h, and you want to define an inverse to it. The point is that, so a goes to 0. So the inverse will be that, sorry, 0 goes to a, 0 goes to a. And if you have increase here, so you will have some increase here. So that's fine. Until here, you actually have one-to-one functions. So it's inverse. You just rotate along this, reflect along this line, and you get it. Now you reach an interval of constancy. Now, what is the inverse? What is the t that corresponds to that? What value of t gives this s? So now this becomes s, and this becomes phi of s, which is kind of inverse of h. The observations that I had made are that take any t, okay, take any t whose value is this. So you can take this one, you can take this one, but I want to take this smallest one, so I take this here. Now you reach this point, for example. What is the t corresponding to s? That will be a jump. So all of this interval map to the same value here, but then all of a sudden when you reach this end and go forward, you have to jump to here. And then let's say there's some increase again somewhere. So each interval of constancy results in some discontinuity. So that is the inverse to that. And actually I can write the formula. So phi of s will be the smallest t with h of t equal to s. I could also take supremum, and then these holes will be on this upper side. So it's whether you get either you get lower semi-continuous or upper semi-continuous. So this phi is a pseudo inverse to the function h. And the punchline of this proof is that the function defined to be gamma composed with phi becomes a continuous function, although phi itself is not continuous. The reason being that throughout this whole thing, gamma is the same. So gamma of this point and gamma of this are equal. So you pick up from where you left. This gap is just insignificant. Yeah. So I give several versions of why all of this works. and hopefully one of them sticks, and you see the picture. Okay, that is how you define the Arclength reparameterization. And the second property again is the key here. Okay, something nice about the Arclength parameterization is that it is actually a Lipschitz parameterization. We had this identity from before. That's easy consequence of the definition of length by taking 2-point partition. Now that we know that if we know that this parameterization gamma, so gamma here is our gamma 0, so I didn't want to keep this gamma 0 the whole time. So if gamma is already an Arclength parameterization, this length then exactly is T2 minus T1. And if you plug it in there, you get that gamma is 1 Lipschitz. So why is Lipschitz parameterizations important? Because by Rademacher's theorem, then gamma prime exists almost everywhere, so that you can talk about this, so that you cannot talk about this. And then you can ask, is this equal to length of gamma? And we will see that for Lipschitz, it is true. But also in metric context, Lipschitz curves are very important because those are the curves for which a notion of derivative exists, the so-called metric derivative. So previous theorem finds significance in light of this because it showed that if you have a rectifiable curve, you can reparameterize it as a 1 Lipschitz curve. That's why it's not really restrictive to require that rectifiable curves be parameterized by Lipschitz curves, or somehow force Lipschitz into the definition of rectifiable curves. Okay, finally, before the end of this first video, I want to talk about curves that are not defined on compact intervals. This allows many new things. So the one thing is that, well, if you have compact, then the image of compact is compact. So curves defined on compact intervals, their images are compact. But with one side open, you can go to infinity, right? So you can have a continuous function from 0 to 1 that goes to infinity, and that's just very simple. Just put 1 over x or something like that, right? Something like this. So for example, here x goes to x and 1 over x. The sine curve is possible because it's not defined on 0 included, but rather 0 and 1, say. This 0 being open allows to just do more and more of this wiggling thing. If you insisted on including 0, then you would have to assign a value at 0. And because you want it continuous, then it's ambiguous where you want to put it. So it's not possible to do a continuous sine curve. So these are possibilities that are allowed by going non-compact, and curves going to infinity is there. Remember, we mentioned that the length definition makes sense for open curves. You just, in your partition, you just do not include the endpoints. So it's still the same definition makes sense, and you can also again ask, define rectifiable to have finite length. An amazing theorem is that if you begin with an open interval and your curve ends up being rectifiable, then you can uniquely extend it to the endpoints. It means that this, in fact, was a closed curve, and not including the endpoints was just superficial. This is saying that you have something like this, and you just did not include in the beginning these endpoints. But according to this theorem, you can fill this in, and you can define it there, and you don't increase the length. sine curve, you cannot fix the zero part, and that means indirectly that it is not rectifiable. Because if it was rectifiable, you would have to be able to assign some value to gamma of 0 in a continuous way, and you can't. So the length of sine curve is infinity, but exercise would be that sine curve not rectifiable. Prove it just using definition of length, which shouldn't be difficult. Find the right partitions. And this also says you cannot go to infinity with a rectifiable curve. Again, if you go to infinity, you cannot assign values to the endpoints. So this is very nice. And proof of this is also not that bad. So by contradiction, suppose that this wasn't the case, and that means if you cannot assign a value, that means your values just wiggle around too much. You go from here, near here, and near here, here and near here. They don't just come together, and they don't come together means there is always some pairs with big distance, pair with big distance, and then length of gamma becomes infinity, because you can find arbitrarily many of these. Okay, but for example, can I talk about, say, an infinite line? It deserves to be called a curve, right? Although it doesn't have finite length. The right notion to do that is the notion of local rectifiability. So on any subinterval that is compact, you have finite length, but in totality, not so. And this allows to, for example, even sine curve is locally rectifiable. It is a curve whenever you restrict to delta to 1 for any delta positive. Okay, that's the story of length, finite length, and Arclength reparameterization. I think this is a great point to stop. My next video will focus on when this formula is true, and you will find out some surprising examples where even the fundamental theorem of calculus fails. Thanks for watching. Please do remember to comment your questions. I encourage you to do some of the exercises here. And until that video, have a wonderful day.